So we have understanding of what I mean by the derivative of a determinant. Derivative of determinant, where determinant, what is the definition of determinant of a matrix X? X is the matrix Xij, where Xij are the entries of the matrix X. So we know that the definition of determinant is a summation. This is a n by n matrix. So this is a summation x1 sigma 1 multiplied by xn sigma n multiplied by sine of sigma which should come here. Okay, and sum over sigma in Sn and 1 over n factorial. So the exercise is find the partial derivatives. Find all the partial derivatives and calculate what the derivative is. Find the derivative of determinant using partial derivatives. Let me assure you, you will not get this right if you try to do it this way. So this is the first example where you will see that thinking of derivatives in terms of linear maps creates much more conceptual, generates much more conceptual clarity than thinking of it in terms of, only in terms of the partial derivatives. Okay, and by the way, finding derivative of a determinant actually is an important object, important thing to learn how to do, especially in differential equations. And as far away differential equations, there are quite a few places where you have to talk about the derivative or determinant. Not just that, you have to apply a chain rule to find the derivative of the determinant. So we'll see if we have time to think about this, talk about this a bit later on. Okay. So there's another map that we should be familiar with. So this is another exercise on similar lines that, you see, so far we are talking about Rn, but we could also think about n, R. This is n by n matrices with entries in R, and you know that this looks like a R to the n squared dimensional vector space. It looks like R to the n squared. Okay, so it is also some R to some power. There is a natural map from MNR to MNR. There are lots of natural maps from MNR to MNR. So there's a map which we will call TR. What is the meaning of TR? TR is a transpose. TR maps MNR to MNR, and TR of a matrix A is equal to A transpose. Or you can have the map which says, instead of transpose, you could say, for example, A squared, S cubed, S cubed, from MNR to MNR, which is S cubed of A is equal to A squared. In general, you could have to the nth power, okay? Nth power A going to A to the power n. A to the power P, A to the power P, for P an integer. The question is, what is the derivative of these maps? what are the derivatives at a point. Now, this first one is something that you should immediately know what to do. Okay? This map transpose is a linear map. The derivative of a linear map at a point is the linear map itself. You've seen this earlier. And the question is, what is the meaning in this setup? What is the derivative of the transpose at a point? So, derivative of the map transpose at a point A evaluated at h is equal to 1. Similarly, the derivative of the map square at A evaluated at h is equal to 1. So this is something that if you should start playing around with and trying to see whether you can understand what these ideas are going to be. Again, all these ideas are important and they will be needed a bit later on. So, the map that we want to talk about here is the exponential map. So, we all know what the exponential map is for functions from real numbers to real numbers. So, if f, so exponential we call, exponential is a map from R to R, exponential of x is equal to summation x to the n over n factorial n equal to 0 to infinity. There is a similar map defined on matrices. So, define exponential from m and r and let it go to m and r by exponential of a matrix A. Remember, this is an n by n matrix. Okay? This is equal to summation A to the k over k factorial k equal to 0 to infinity. Now, there's something to be done here because you have to understand that that sum makes sense. So, maybe we'll get into that a bit later on. But right now, we'll take it for granted that that sum actually converges. M and R is a Banach space. This is a Cauchy sequence. Every Cauchy sequence converges in a Banach space, and therefore that exponential exists. It's a different question of how to actually calculate it. So, this is the definition of exponential. And the question is, what is the derivative of this map? Maybe you won't be able to talk about the derivative at every point, but at least what is the derivative of this map near the identity? What is the identity? The identity is the additive identity. Okay, M and R is a vector space with the operation of addition. The additive identity on M and R is 0. So what I want to, so the question you want to ask is, exercise, evaluate the derivative of the exponential map at a particular point, at the point 0. Where is this 0? This 0 is the 0 matrix. So this 0 is the matrix in M and R. What should this be? This should be, remember, the derivative of a function at a point is a linear map from here to here. So I should be able to tell you what it does to a point h. What is h? H is a n by n matrix. So this also is in n and R. And what you should try to convince yourself is that derivative of the exponential at 0. See, what is d by dx of e to the x evaluated at x equal to 0? The derivative is 1. So the derivative you would expect for exponential map at 0 evaluated at h should be the identity map. So this should be equal to the identity acting on h, which is equal to h. Okay? d by dx of v to the x at x equal to 0 is 1. That is what I'm writing down. This is going to take a little bit of time, but anyway, it's worthwhile thinking about it. So this exponential map is something that arises everywhere. And finding the derivative of the exponential at a point is a very important concept, which you will need over and over again. So in fact, this is a place where, again, you should try to think about what you would mean by finding the derivative of a function in terms of partial derivatives. For example, if I put n equal to 2, I have an exponential map from n2r to n2r defined by that, and I want to find out what the partial derivative. So the exercise is find partial derivatives of exp. In other words, if the matrix A, if the element x in n2r is x is equal to x11, x12, x21, x22, find dx by dx11, dx by dx12. This is an impossible task. But anyway, you should try to think about how would you find the derivative of exponential evaluated at a point x. This is practically impossible to do. And this is again a place where you will understand that it is imperative. You have to think about the derivative as a linear map between these two spaces. Okay, so there's one more map that one has to think about here. So we have exponential, we have multilinear maps, and the next map I want to talk about is the inverse map. So, remember when you have a function from R to R given by f of x is equal to x inverse. Then, we have all learned a long time ago that, recall, if f of x is equal to 1 by x, f is from R, I will subtract 0 to R, then d by dx of f of x, which is d by dx of 1 by x, evaluated at x is equal to a, evaluated at x equal to a, is minus 1 over a squared. A is in R minus 0. d by dx of 1 by x is minus 1 by x squared. So this is something all of us knew a long time ago. So what is the exercise? So I want to see what this means for matrices. So again, I must talk about matrices, okay, for which the inverse exists. So I look for all those matrices, n by n matrices, whose inverse exists. This set of n by n matrices whose inverse exists is given a fancy name. It's called GL and R. So GL NR is equal to all those A's in M and R, n by n matrices for which the inverse exists. And it is clear that you have come across the statement that the inverse exists if and only if the determinant of A is not equal to 0, and therefore this is equal to det inverse of 0, where determinant is the determinant map from M and R to R. Sorry, det inverse 0 complement, which is det inverse R minus 0. Every invertible matrix has a non-zero determinant. Now, this set is open. Determinant is a continuous map. The inverse image of an open set under a continuous map is open, and therefore this set is an open subset of M and R. There's a reason why I have to say this, because if you recall in the definition of determinant, so far I was thinking of functions defined on the whole of Rn, but I didn't really have to have it defined on the whole of Rn. I have to define it, I should be able to define determinant for any set where if A is in that set, A plus H should also be in the domain for all H which are sufficiently small. That means that the set on which I can define determinant, hope to define determinant, are the open sets. So this GLNR is an open set. Now I'm going to have is open in M and R, and therefore it looks like a R open set in R to the n squared. Then I can talk about the map INV. What is the map INV? It is a map inverse, which will go from the open set GL and R, and it will give you the inverse of some matrix in GL and R is an element in M and R. In fact, it is an element in GL and R itself, invertible matrices. The inverse of an invertible matrix is invertible. But I don't want to think about it in that way. I want to think about it as M and R. This is an open set in a n squared dimensional vector space. This is an n squared dimensional vector space. And therefore, I should be able to talk about what I mean by the derivative of the map INV. This is the function. INV is the function from this vector, this open set in Rn squared to this R to the n squared. So I can talk about the derivative of the inverse map evaluated at a point A. Where is A? A is an element in G and R. So the derivative of the map INV, the function INV, evaluated at a point in GL and R. What should this be? This should be a linear map from the whole space to here. So this is a linear map from M and R to M and R. Now I'm jumping a little bit here. GL and R is an open subset of M and R. M and R is a vector space. The derivative of the inverse at a point in GL and R is a linear map from this vector space to this vector space. And I want to find out what this map is. So the exercise is that the derivative of I and V evaluated at A, this is a linear map from here to here. So I should take a point H. Where is H? H is here. So this H is in M and R. And what I should get should be an element in M and R, and it should be linear in H. So, let's go back to this definition of d by dx of 1 by x at x equal to a is minus 1 by a squared. Remember, in one dimensions that minus 1 by a squared represents a linear map. It represents a linear map h going to minus 1 by a squared times h. So I should write something down here that corresponds to minus 1 by a squared times h. Minus 1 by a squared times h. Okay? So I have to play around. So this, what does this mean? This means minus a into the minus 2 times h. And can this be correct is the question. Now here you must try to think about, if this is what is the case when n is equal to 1, what should the general statement be? So the general statement should be something that becomes this when n is equal to 1. And the exercise is that derivative of this is equal to, so the statements that I've written here are wrong, okay, and it should be equal to minus A inverse H A inverse. So I hope you will try to do this. There's nothing very difficult in this statement, and it follows from the following kind of argument, which is the same argument that you use here. And that argument is that that 1 over x plus h minus 1 over x is equal to x minus x plus h over x plus h into x, which is equal to h over x plus h into x, when you have scalars. Only trouble is you don't have scalars, you have matrices, and matrices do not commute. So you have to worry about which order you're pulling things out. So just remember, the proof of this is the same as the proof of this, with the understanding that you have to take care about commutativity of matrices or non-commutativity of matrices. This is a very good exercise to try and see whether you understand what is meant by the derivative. So this is a place where we'll have a bit of a break again. So the last time we were talking about the map inverse. The map inverse is a map from invertible matrices to M and R, given by I and V of A. A is an invertible matrix, is A inverse. This is exactly the same as for real numbers. It is x going to 1 by x. d by dx of 1 by x is minus 1 by x squared. This is what we are trying to understand. And the statement is that the derivative of the inverse at A is a point in GL and R. This derivative of the inverse at A, this quantity is a linear map from M and R to M and R. So derivative of the inverse evaluated at a point is a linear map. So it should be linear in this variable h. And I want to say that the derivative of the I and B evaluated at A, evaluated at a matrix H, remember all these are n by n matrices, is equal to minus A inverse H A inverse. This is linear in the H, please note that. Very good. And I had mentioned last time that this is basically the same proof that you had in 11th standard when you're trying to prove d by dx of 1 by x is minus 1 by x squared. What does it start off with? It starts off with a plus h inverse minus a inverse. Remember, h is small. What do? I pull this a plus h inverse on the left. So I get a plus h inverse identity minus, there's no a plus h inverse here, so I must write a plus h and a inverse. But there's still a inverse, I have to get rid of that. But I can't get rid of it on the left, so I get rid of it on the right. So I multiply this, I pull out this a inverse here. And what do I have remaining? A minus a plus h, which is equal to this a and this a will now cancel. And then you continue trying to think about this. So just try to think about what you had done in one dimension, and the same proof works here. Be careful about commutativity. And the exercise here again is, even in the case, try to do this calculation of finding the derivative of the inverse. So what is the definition even when n is equal to 2? N equal to 2, I n v of x, which is x2, x21, x22. What is it equal to? It's equal to 1 over x11, x12 minus x21, x11, x22 minus x21, x12 into its cofactors, which is the cofactor which will be equal to, I think it will be what is it? I have to interchange this x22, x11 and x21, x12 with the right sign, x12, x11, x22, x22, x12 and x11, x12, x12, x22, so I should put a minus sign here, x21, x22, x22, x21, x21, x12, x22, I think that's correct. Okay? And then find the partial derivatives. Find all partial derivatives. So even when you put n equal to 3 or n equal to 4, you're going to have lots and lots of problems. So partial derivatives does not work here. This is one thing that you have to keep in mind. So you have to think about the derivative as being a linear map. And we should continue from here next time.